Hi guys, welcome to the first lesson on oscillations. My name is Brenda, and I am your physics tutor for today. Physics is quite a complex subject, but I have seen students struggling with oscillations the most. This is why, I will cover the basics in this video to help you get a solid grip on oscillations. Let's get started. Oscillation is the to and fro movement of an object between two positions or states. One oscillation is a complete movement, whether side to side or up and down, over a specific period of time. Consider the movement of the pendulum of a wall clock. Initially, the pendulum is at its equilibrium position. If you displace the bob of the pendulum from its equilibrium position, a force acts on the body trying to bring it back to its equilibrium position. The force acting on the body is known as restoring force, and it gives rise to oscillations. Oscillatory motion is always periodic, that means it takes place within equal intervals of time. Other examples of oscillatory motion are the movement of artificial and natural satellites around the Earth, the motion of the comets, to and fro movement of the swinging pendulum, the phases of the moon, etc. Well, there are three main types of oscillations: damped, oscillatory motion; driven and damped, oscillations, simple harmonic motion. Damped, oscillations. When the oscillations of a body eventually die away due to frictional energy loss, it is known as damped oscillations or damped simple harmonic motion. Examples: the oscillations of a pendulum, electromagnetic damping in galvanometer, and electromagnetic oscillations in the tank circuit. Driven and damped oscillations. The only way to maintain the amplitude of a damped oscillator is to continuously feed external energy into the system to offset the frictional loss. Such a steady oscillation is known as driven and damped harmonic oscillation. For example, if we push a child on a swing in the same direction, the amplitude of the swing increases, until the external force equalizes the frictional forces acting on the swing. Thus, the amplitude of the swing increases a little every time we push it against the frictional forces. Simple harmonic motion. Simple harmonic motion is the periodic to and fro movement of an object along a single line. Check out this pendulum here. When we swing it, the pendulum moves to and fro along the same line. This movement or motion is a simple harmonic motion. Here is a spring that is fixed at one end. The spring is at its equilibrium position when there is no force applied. Now, when we pull it outwards, the spring exerts a restoring force towards the equilibrium, as you can see in the image. When we push the spring inwards, the spring again exerts a restoring force towards the equilibrium position. In each case, we can see that the spring exerts the restoring force towards the equilibrium. Let the force be F and displacement of the spring from its equilibrium position be x. K is the constant here. Hence, F equals minus kx. The negative sign indicates that the restoring force acts in the opposite direction. Common terms in simple harmonic motion. Time period or T. It is the time taken by an object to complete a full cycle of periodic motion. For example, it is referred to the time taken by a pendulum to complete one full back and forth swing. Frequency or F. It is the number of oscillations that are completed each second. A full 360 degree is 2 pi radians, and that represents one full oscillation. The amplitude or A. It is the maximum displacement of a particle in either the positive or negative x direction. Calculating the time period of an oscillating spring. Remember, time is denoted by T and is measured in seconds, M denotes the mass of the object and is measured in kilograms, and K is the spring constant. The equation is, T is equal to 2 of pi, multiplied by the square root of M, divided by K. Calculating the maximum displacement of an oscillating spring. The equation for calculating the maximum displacement is, x is equal to a sine omega t, where x is the displacement of the object from its mean position, a is the amplitude, omega is the angular frequency in radians per second, and t is the time in seconds. Remember that omega is calculated by the formula, omega is equal to 2 pi f, or, omega is equal to 2 pi divided by the time period. Graphically, the displacement can be in the x direction or the y direction, depending on the situation. If the mass of a spring system and its motion were measured correctly, its xt graph would be a near-perfect sine wave or sinusoidal shape as shown in the graph. Hence, simple harmonic motions are always sinusoidal. Calculating the frequency of an oscillating spring. The equation for calculating the frequency is, f is equal to the inverse of the time period, where t is the time period and is measured in hertz. Calculating the acceleration of an oscillating body. The acceleration, a, of an oscillating body is given by, a is equal to the negative of omega square multiplied by x. Applying the equation of motion, f is equal to mass multiplied by acceleration, and substituting the value of a in this equation, we have, f is equal to minus m, of omega square, of x, equals minus k of x, where k is equal to m, of x square and is also known as an elastic constant. The kinetic energy of the oscillating body. Kinetic energy is the energy possessed by the body when it is in motion. The kinetic energy of an oscillating particle is, k is equal to half of ma square, omega square, sine omega t, plus delta square. The potential energy of the oscillating body. Potential energy is the energy possessed by the body when it is static. It is denoted by U. So, U equals half kx square, or U is equal to half ka square, cos omega t, plus delta square. The total energy of an oscillating body, E. E equals k plus U equals half ka square, sine omega t plus, delta square, plus cos omega t, plus delta square, is equal to half ka square. The total energy of the oscillating body is constant and is equal to the potential energy when the string is stretched to its maximum value. If we plot the kinetic energy, potential energy, total energy in the x-axis and the time period along the y-axis, the graph looks like this. As shown in the graph, the energy constantly shifts form between kinetic and potential. Initially, the mass is at its maximum value, and the velocity is zero. So all the energy is in the potential state. With the change in time, all that potential energy has gone to kinetic energy as the mass passes through x equals 0. It starts slowing down as it heads over to negative x. However, when the spring is maximally compressed, the energy is all potential again. I hope you got a thorough understanding of the basics of oscillation. If you have any query, you can easily get in touch with MyAssignmentHelp.com for further assistance with this subject.